Today. So Mark Moeller is the first speaker, as you can see, from Cornell. He'll be talking about, well, I'm sure you will repeat what you're talking about in a minute, so I'll just let you go ahead. Thank you.
Oh, there we go. Hello, everyone. I'm Mark. I'm a PhD student at Cornell, and I'm also an intern at Galois this summer. So if you're interested in Galois, please come talk to me. And I'm excited to tell you today about active learning of symbolic NetKAT automata. So in the networking domain, we can think of the routing policy installed at the various switches as just a program. And that program is distributed in some sense, but in another sense, it just takes packets as input, it filters or perhaps updates fields in the packet, and then produces output packets. But we can just think of that as output of the program. Okay, and as a program, of course, it's very easy to create bugs that are routing behaviors we don't want. And so we might have some verification questions that we want to ask about the programs installed, the routing policies installed on our switches. In particular, an easy one is, are all the hosts reachable from every other host, for example? Okay, and a way to do this is you write down a precise specification for the thing you want to check, and then you do some verification query to say, does the policy in place implement this completely? And NetKAT is a DSL for specifying routing policies that has the main benefit that everything can be compiled down to an automaton, and then doing these verification queries amounts to doing automata equivalence, and that answers this question for you. I will say that because it was developed at Cornell about 10 years ago, it's also a big red cat. That is the joke there. Okay, and what if we have, there's a main problem with doing this analysis sometimes, and that is, what if in our network we have some unknowns? In particular, we might not know the precise implementation of all of the switches we run. Maybe we got it from a hardware vendor, and the internals of how the switch isn't completely clear to us, or even we have a configuration, but we're not sure of the semantics. I might want to investigate that to be sure of the behavior of my network. Or in another situation, I might not yet have a precise spec, but I still want to build a model of my own network for the purpose of understanding its behavior. Okay, so to be clear about what I mean, I'm interested in this question: can we build a model of the network by observing traces through it? So in particular, we're not going to be allowed to look at the switch configurations, or the program text, if you will. But we can send packets from the hosts and observe the resulting trace through there. I'm assuming that we have some network telemetry, such as traceroute or something along those lines, to observe the behaviors actually being exhibited by my network. Okay, and this sounds like there's a long line of work on active learning of closed box systems, where you're really thinking of a single system most of the time. But the way this works is that a learner sort of hypothesizes that the closed box system is modeled by a DFA, and the L-star algorithm, famously due to Englund in the 80s, basically gives you a way to systematically query strings, like, is this a valid string by the DFA driving the system? And the thing will say yes or no by observing its output. And then you update some data structure and make progress on determining what the DFA is this way. So the updates to your data structure will give you more strings to query, and you query these strings and observe their behavior, and you iterate on this and update your behavior. And eventually, it gives you a way to conjecture a DFA. And when you do that, the formal model that Englund devised said that the teacher will give you a counterexample. And so, okay, in this case, some string that your hypothesis misclassifies that is the wrong behavior of the system. And then you update your data structure and keep iterating. And eventually, you terminate when you get the exactly correct DFA. Okay, great. In fact, L-star has already had some success in networking, but it's really been focused on end hosts. So these were projects where they were able to derive the DFA at the core of an end host implementation of TCP, SSH, quick, by basically querying traces that corresponded to packets and then deducing how the end host implementation of these protocols worked using L*. So because of this success, we had the hypothesis that this technique would work for entire network behaviors, that is, across multiple switches. Okay, so my solution here is to adapt L* to NetKAT Automata. And the picture works exactly how you think, that instead of a DFA in there, there's a network under test. And now the strings that before were sort of a formal alphabet correspond to a series of packets that represent a trace through the network. And by proposing one, I really mean seeing if this is a behavior of the network by sending a packet and seeing if I observe this. Okay, and then I get yes or no answers to that. And at least for our formal framework, you can query, this is a cartoon of a NetKAT automaton, and again, you get the no, yes if you're correct and you terminate, or no in a counterexample. Okay, and we can talk about the realism of the conjecture in a bit. Okay, so one key challenge I want to point out about this process, that is of trying to do L* in this richer domain, is that in DFAs, transition symbols, well, you have the transitions labeled by concrete members of the alphabet. And if you were to just naively translate this over to NetKAT, the packet space is enormous, and already the machines you build are going to be enormous for the same reason. Okay, so I have an insight about this, which is that you can try to represent the packets symbolically. And I presented a paper of ours with Jules, who you'll see in a moment, and others last year at PLDI, where we do indeed represent transitions symbolically, and this works great. But the trick here is really to thread it through the learning process and come up with conjectures under this scheme, and that was one of the big challenges of this work. Okay, a second key challenge here, and I think in some ways this is the bigger one, that NetKAT is great about representing update behavior for packets. And again, to explain what I mean by that, I want to use the example of DFA, just like we did in the last slide. And that is, if we have a DFA like this, and a short string AB, well, I can run this string, and you know how to do this. I read the A, and I get to Q1. And the point is at this point that when I look at the symbol that's next, the B, it doesn't matter how I got there. I could have gotten there by a series of A's or even a B. But independent of the first move, the B is how I get to Q2. But that property isn't how NetKAT works. NetKAT is about updating the previous symbol. So to give you an example, and here's a little NetKAT program that's sort of motivated by this real-life drawing. It's the same one we saw before. If I'm at, what this transition says is that if I'm at switch A, and if the destination is host 3, then this particular forwarding policy says that I should send that packet out on port 2 to make progress towards 3. And moreover, the point that I was trying to make was that if the last symbol we saw was the first packet, so it's just a triple in this case, that I'm at switch A and my destination is 3, and I was on port 1, this transition is denoting the update of the port, the physical location of the packet on the device, but this dependency is on that previous packet. And so it's not the same situation as the DFA. And of course, L* relies heavily on this independence of the successive symbols, whereas in NetKAT, we really do need to model this update behavior. And that's one of the main challenges of designing the learning algorithm. I have an animation out of order there. Okay, so the naive answer to this is just to build the DFAs. And what I mean by that is that the update behavior of the packets really, the previous packet could just be modeled by state, right? I'm saying that there's this complicated relationship between successive packets, but I can just roll all of that into the state space, and build essentially what's a large DFA and run L star. The problem, of course, is that the problem, of course, is the enormous state space blowup that results from doing this technique. Okay, so if I just do this naive solution, there is a way that this all works, but it creates a large intractable machine. A better answer is to build a fragment of this naive machine based on only the observations that I've seen so far. So as the learning process develops, there's only a few packets that I'm seeing, and so I build basically a fragment of this machine that doesn't make sense. It's a partial, it's partially defined. Whereas L-star would have me exhaustively explore the space. Here I just build the fragment. And then I generalize it to a full symbolic automaton by essentially looking at the evidence that I have and building those symbolic transitions based on the positive and negative example traces. Okay, so then I have this full symbolic automaton. And the point was, and this is where the animation was out of order, I apologize for that, that this brings us back to my original goal, which is now that I have a complete symbolic automaton, I can compare it against specifications using our verification queries from the beginning. Okay, so we built all of this in an OCaml implementation. The artifact is findable through the paper link. And I benchmarked it on the topologies from the Internet Topology Zoo. So there's a set of 260 or so topologies, and they come from primarily ISP backbone networks. And what we did is we laid a simple forwarding policy on top of these switches and tested reachability queries we ran the learner on these forwarding policies, and we were able to learn the policies in place for the entire network for between half and 2/3 of them. But this is the first tool that we know of that does this, and so we're pretty excited by these results. That's within a 30-minute timeout, and this gives you an idea of the membership and equivalence queries as things scale. Note these are log-log axes. Okay, there's a lot more in the paper. In particular, the naive solution that I described that I was saying was essentially DFAs, it's a little bit more subtle than that, and I'm calling it a naive learner, but actually it took us a fair amount of effort to get there. And so the fun theorem we prove is that we do learn a uniquely minimal solution, even though it's practically large. It's unique for the representation and smallest, and we do that through Myhill-Néraud theorem. That's along the lines of what Dexter Cosin proved for automaton-guarded strings more generally. Okay, and then the way the algorithm works, there's this subordinated symbolic transition learner for the transitions. That's what I was saying, sort of generalizes the few packets we've seen to a complete symbolic transition. But this is actually useful in its own right when you only care about the input packets and the output packets they produce. If you don't care about the full trace behavior of the network, then our subordinate learner is interesting and able to solve this problem for you already. Okay, and then finally we prove correctness of the symbolic automaton learner, which is to say we prove termination because we conclude by reaching a yes answer to the conjectures. That's correctness. Okay, and then a couple remarks on future work that I'm interested in. The symbolic version of the automata do not have unique state minimal forms, and so there's an interesting question of, for a given application, which one would be the most useful one to learn? That is to say, you could have different symbolic transitions at various places in the automaton, and for your application, it may matter what those look like, and you have some choices as the algorithm goes that we more or less make arbitrarily, but that could have some interesting answers. And then finally, I'm interested in the question of what if we don't have full network telemetry? What if some packets are not observable to us or have missing information? could we still make progress, and what guarantees could we give in a setting like that? Okay, and at that, I will take questions.
So maybe best if you come up to the microphone so that we can record it for the posterity. Thank you.
Hi, Chris Casankino, Jane Street. I wondered in your empirical evaluation whether there were particular characteristics of networks that made them hard to learn, or whether there was just scale purely.
I see, that's a good question. I definitely saw a relationship to scale, and so I will say that was the biggest factor that I noticed. I would have to do some more investigation. It's an interesting question.
Thanks.
As to what would make networks harder to learn.
Hi, Mark. Jules Jacobs from Cornell. Could you show the graph with timing again?
I can.
So I just wondered, how long would it take to solve the largest topology zoo?
That's a good question.
Because you have a very nice line here.
Yeah, you're saying I should, if I just draw the line, where would the crossover be? Yeah. I don't know. I'll have to get back to you on that. That's a good question.
Cool. Anyone else? I have a silly question. So if I'm working for a switch company, I use P4 and I have my very custom for whatever company I'm working for ways to know the tables and everything like that. And I kind of look at this, high level stuff, and I want to sort of learn as a developer within a network switch company, how can I verify what is happening with me with the custom router stuff, some P4 language which you can understand, but what would it take to bring it down to sort of practical explanation for me as a,
In terms of, I guess I missed the part that you...
How do you see it if you were to explain it to a network switch, I don't know, is it network switch engineer or someone who works on this? How can they use this? What
I see.
Would make it practical for them?
How I think of this work is a way to guide your testing in a way to guide you towards having a complete understanding of your system, and that model that you build would tell you all of the behaviors of the thing you wrote down.
Despite some proprietary ways of looking up the switch tables or routes, because this is going to be dependent on the company?
I say despite that because ultimately the model we build will be based on the behaviors that actually you observe. And so in some sense it's ground truth regardless of the proprietary design of the switch itself.
Okay, that's fine. I think we are good on time now, so we can finish. Thank you very much. Thank you very much.